Hey, so if you're here, say something in chat. We don't have to do that for everyone, but just to get a sense. Okay, I'll wait another minute or so to see if anyone else comes. All right, we got a good number. So let's talk about OR tools. So the background on this is that the Computer Science Club at Stetson, which is active this semester, so you should definitely be aware of that. They're doing these talks, and they asked the professors if they had anything to talk about. And I came up with two ideas. So both of these ideas are actually based on a project that I've been working on in my sabbatical. So I've been kind of intimately familiar with the OR tools library. I don't know like all the dimensions of it. I've only really used one aspect of it, but used it a lot. So I thought that would be pretty easy to talk about. And then the second thing is talk about React for JavaScript. I've not used React Native, which would be for like phones, but it's probably pretty similar. But React JavaScript for making websites that are highly responsive. So they seem to be like normal applications where they react to all the things that you do. And that will be, I think, the 23rd or something like that in a few weeks. So this one is how to use a AI library for doing interesting algorithmic problems without really going through all the tedious effort of writing an algorithm that you might see in like the algorithms class. That's been done, like the search techniques, the optimization techniques, the dynamic programming, all that fun stuff that you might learn in that class has been implemented as a library. So we get to use that and then just solve the problem that we have in front of us. And for an example, I went to the codility problems, which are like programming problems. I guess they're used for interviews. I'm not sure. Because the active problem, like you're supposed to do it live on the interface on the website, but then they have all the old problems. So I went through some of the old problems and solved them with this OR tools technique, and that's what we'll cover. So I have there are four that I can cover, and if people put in chat that they get tired of, or I mean, they could just drop off. But if you want to cover like a different one on Codility, which I'll show you in a second, we could do that. And then there are two that I glanced at but haven't solved yet. So if you want to like go through the solving process together, hopefully that would be interesting. It could be the case that don't know how to solve it and it will take a while and I have to go like sleep on it or something. So that might not work, but we'll see when we get there. And so feel free to use the chat to ask something or tell me to go over something again. I'm using Linux, but it doesn't really matter. You could use Windows or Mac. It's a Python library. It actually supports Java and C++ and .NET, I think, as well. So you can pretty much use whatever system you want. And OR Tools is open source. So if you ever make a commercial product with this, you're free to do that. It's Apache license, so you don't have to release your code or anything like that. And I just wanted to show the front page here because OR stands for Operations Research, which is, it's a more mathematical concept. We actually have had a course in the math department related to this subject. So the computer science AI people don't really own this topic, but we do use it a lot. So that's what OR is. And it supports problems you've seen in algorithms if you've taken that course. What companies use this? Robbie says, I think Google uses it for their routing. You see here vehicle routing. I haven't seen a list of companies. The technique is definitely used. There's other tools like from, is it IBM Cplex? There's one called Cplex. It's very expensive though, but that's definitely used by a lot of companies. And there's also Gurobi, which is also expensive, and that's used by a lot of companies. And then there's some other open source ones. So the techniques that OR tools uses is similar to these other tools. So it supports, we're going to do constraint programming, but there are other things you can do that you might have heard of, like linear programming and so forth. If you've heard of knapsack problems, which is where you only have so much space, like say moving trucks, and you got to put, like if you're UPS, you got to put the boxes in the trucks in an optimal way, then how do you do that? How do you find the optimal arrangement of the boxes efficiently? And then things like routing airplanes to make most efficient use of fuel, and vehicle routing, literally like you have to hit so many points in so much time. Traveling salesman problem, you have to hit all these points without repeating. Especially scheduling. How do you arrange people's schedules so that there's always a certain number of people working? Or job shop scheduling. How many machines need to be running at what times and which parts go to which machines in what order. All these kind of things. They're all some kind of optimization problem. So, and that's why it's called operations research. It's people who focus on the operations of factories and people, how do they find the best technique to do something? And so that's a search problem, and that's why these tools exist, to make that easier. Networking problems with the optimal path through a network and so forth. And the other thing I want to show you, there's all these libraries inside that we're not going to use except for SAT, but the others are for different kinds of problems, so just be aware that they exist. And there's lots of examples in lots of languages, and the install is pretty straightforward. I think the install's here. So if you wanted to like follow along, you can use pip for Python. It's just, you can run this command or just literally pip install OR tools. So as far as the setup, let's just pip install it and you're good to go. And now let's talk about what it can do. And first, actually, I wanted to just show you, I'm not going to type out this example because it's pretty simple, but Crypt Arithmetic is one of those classic puzzles, you know, where you say these two letters plus these two letters plus these three letters equals these four letters. And so what are the numbers? And they all have to be different maybe. And so you have to find what the numbers have to be to add up correctly. Not very interesting, but this is how you would do it in OR tools. And as you see, there's similar implementations in the other languages. So you make a variable, integer variable, and you say what possible ranges. You say that they're all going to be collected together, and then they all have to be different. The values have to be different, and it has to add up correctly, where base is 10. So it's just representing the problem constraints with certain variables, and then you tell it to go solve it. Ignore this. This is just to print all the solutions. You just say, now go do it. And you get all the answers. So that's it. You set up the problem using very constrained environment. You only have very small number of tools to set up the problem. And then you tell it to solve. And if it's a big problem, you just sit there and wait. It could take hours. It could take days. It depends on how complex the problem is. But the point is, once you set it up, CP solver, which is what we're going to use, runs its search. You cannot stop it part way and inspect the results. You can't say, throw an if in there. If you reach this, then stop or print or whatever. You don't have control over anything. Once you tell it to go, it just goes. So your role is to set up the problem. And you need to sometimes be aware of how it's solved so that you set it up in a way that actually works or doesn't take forever, because you could set it up better or worse, but you're not writing the algorithm to solve it. That's what OR Tools gives you. So Jojo Rocco says, short lecture on Knapsack Problem, has a YouTube link. Yeah, so about interview problems. So the setup here, what I'm trying to convey with this stream is you can use this in some cases, like if they let you use it, if they let you install a Python package, to get this like superpower that most interviewees wouldn't know about. So I don't know if you really have the chance to do this live during an interview, but the point is you might be able to at least talk about it and say, look, I know you want me to solve it with a bunch of for loops and a bunch of if statements and arrays and all that nuisance stuff. I can do that if you want me to, or I can set up the problem as an optimization problem with constraints. They call it constraint programming, CP. I can do a constraint programming solution, and then you can handle huge problems. Like it's designed for very, very large problems. In other words, you might have a simple problem when it's small, but then if you make 100,000 things to put in the truck, now it's like virtually impossible to solve efficiently. So you need a tool like this to do it as well as possible. I mean, this is like active research code. It's constantly being updated with whatever algorithms are being discovered out there. So it can solve real world problems. I'm using it to solve a course scheduling problem, like when you should take certain courses. It's got to know about prereqs and when the course is offered and all that. That's what I used it for. But in an interview style situation, the problems they often give you work really well with this approach. And most people have no idea this approach exists. I'd say most people interviewing. So if you bring this up, or you even have the chance to solve it this way, that's interesting, right? You have an interesting thing about you now. So that's the motivation behind this. You'll probably still be challenged on actual algorithmic ways to do things, but this is a thing you can talk about. So for the examples, if you go to codility.com and then under login, you don't have to make an account, but if you go to login for programmers, skip the login, just go to challenges. And they have like years of challenges. So it appears that if you start the current challenge, which just started actually a couple days ago, you can use their editor online to type your solution. And you can choose Python, you can choose whatever, Java, I guess. And then submit it, and they will check against the examples, and they'll check against big examples that you don't know about, I think, and tell you if you got it right. And then you're on the leaderboard and all that jazz. But their Python implementation doesn't have OR tools naturally, and there's no way to install it, I think. So you can't literally solve the active challenge with this technique on Codility because they don't expect people to do that. But we can go through the past ones and see what we could have done if they had supported it. So the first one I want to address is Silver 2020. And what you see is like the leaderboard and everything, but go to the view link and you'll see the problem description. And every one of these that I've looked at are some sort of search, like find the least number of something or the most or whatever. And they give you a problem set up, and then they say these are the things that can be done, like you can move this over here or whatever, and then find the optimal such and such and make it efficient. So if the problem is massive, like huge arrays, it's still efficient. And a lot of those fit very well into the paradigm of constraint programming. So let's just look at this first, and then I'll start introducing the aspects of constraint programming. So the challenge is, from a given set, choose as many rectangles with common side as possible. That doesn't really explain anything. There are n rectangles, and the kth rectangle has size a by k. So basically, they're going to give you an array and a second array that are integers, and there are n things. So these two arrays represent the size of the rectangle. So it's like width times height. So here's an example. The first rectangle is 2 by 3. The second one is 3 by 4. Third one is 2 by 4, and so forth. Oh, I think I got that mixed up. 2 by 3, 3 by 4, 2 by 2, and so on. So you have these rectangles. We want to arrange as many rectangles as possible into a strip like this. So I guess the order could matter. I don't think the order actually matters here. It's just how many can you put together. And the rule is, the constraint is, rectangles can be arranged into a strip if they all share the same side length, so like 2. So the height needs to be the same all the way across. But you can flip a rectangle, so you can switch its width and height. So the question is, what's the maximum number that can be arranged like this? So some won't be included. So it's an optimization problem, and it has constraints. That tells you it might be good to use constraint programming. So we have to set up the problem now. And what that involves is making variables that the thing is going to find the answers for, and then telling it to solve it, and putting the constraints and then telling it to solve. So what are our options for solving these problems? So if you go to reference on the OR tool site, Python reference cpsat. So this is your world if you're using this library. On the right here, a lot of these are not actually relevant, but the ones that say add, not even all those, and the ones that say new, that is all you have to set up this problem. So you'll see as we get into this, but what happens is you start to feel like it's a puzzle. You have all this in front of you, like you're looking at the whole screen. This is all that exists. You don't have loops. You don't have for loops. You don't have if statements. You can't use those when you set up the problem. You can only add variables and constraints. So, and you can't just write constraints as if statements or something. You have to use what's on this list. So it's a puzzle because it's all right in front of you on the table. You're just staring at all these pieces and you have no idea how to put this thing together. You kind of know what you want to achieve. You have all the things, but you don't know how to organize it. And it makes me think of games too. Games do this really well, where you're in this situation, you trying to get somewhere or whatever, and it gets in your head, and you even like start dreaming about it because you can understand the whole situation. You just don't know how to solve it. So it's so relieving, in my feeling, to be in the situation as a programmer. You get to ditch all the printing statements and the print formatting and the XML files and the JSON files and the various loops you have and how arrays work and whether you should use a set or not and all this stuff. That's just irrelevant. You only have the tools provided by the OR tools library. So it's small enough and challenging enough that it really makes you feel like you're really programming again. You're not just building you're not just calling APIs constantly and putting a bunch of try catches or whatever. You are programming now for real because it's a deep puzzle. So what we have available to us are things like make a new integer variable and add some constraints like something has to equal something else, or something's true or false or whatever. So let's actually just get started on that rather than just go through this whole list and tell you one by one what they do. We need to first put the input data in our code. So we'll call this rectangle strip, Python file. We'll just do the one import. That's all we need. CP model for constraint programming. Oh, there's a question. Yep. So they are just functions, but you're setting up a configuration that then it goes to solve. And if you don't set it up right, it won't find solutions. So you'll see what I mean in a second here. So let's put the example data that it gave, 2, 3, 2, 3, 5, and so forth. Okay, so we're starting with this. Now we have to start thinking. What are the variables? Like, I mean, here's a variable, but that variable OR Tools doesn't care about. It's been established to be equal to 1. So it has nothing to do with that. It's not going to choose the value of X. What I want are the variables that OR Tools is going to assign the value to. These are the things I don't know about. Specifically, like which rectangles are in the strip and whether or not each one of them is rotated. So, and actually what the height of the strip is, because the whole question here is, what's the height that they all have to match on? So that's a variable. I don't know ahead of time what the height is going to be. It's going to be one of these numbers. So fair enough. It's not important to me that it's one of these numbers, but I don't know what it is. And I want the solver to choose it for me. So that is our first variable. Say new integer variable. We'll do ints and we'll do booleans. Ints, you have to give the range. The minimum height is 1, I presume. Actually, I think they tell us. The arrays A and B are going to be 1 to 1 billion. So fine. That's what they say. And you have to give a title for the variable. Now, you never really see the title that you give unless you force it to print debugging information, I guess, or when there are errors, but you have to give a title. Now, I could tell the solver, okay, maximize strip height. Here's the variable. The constraint is its range is 1 to 1 billion. My goal, optimization goal, is maximize it. So guess what it will say? Strip height should be 1 billion. So that's obviously too trivial to run as an example, but technically you could do that and say that you're using constraint programming. All right, now, actually I can't say model yet. I have to say model equal, I have to make a new model. Okay, so there is a variable. Now I need to ask about every rectangle on this list, the 5 in this list. Am I going to include this one in the strip? And if I am I going to rotate it? Or basically I can say, am I going to include it not rotated, or am I going to include it rotated? And if I include it one way or the other, that's dictating what that strip height variable equals. So I'll put a constraint saying, if you include this rectangle, the height of this thing is the strip height. It has to be. Or you can not include it, in which case we're not saying anything about the strip height. So that's our constraint. But before we can do that, we need to make the Boolean variables to say yes or no, is this rectangle included in the strip? So we'll go through the list. We actually will have a loop, I suppose. And we're going to want to collect these variables, I think. So we'll just make a list that will keep track of all these Boolean variables. So for each position in the array, we're going to go through all of A and all of B. We're going to say you can include, so this position in the array represents a rectangle. You can include this as is, or you can include it as rotated. So we'll make a Boolean for each case. We'll just make it and put it in the array or the list at the same time. New boolvar. And that's my message, because it forces me to give a message for that variable, what it means. And rotated in strip bars. All right, so we have two variables for each rectangle. Now, you say it's a Boolean variable. I do not say what it equals. That's the whole point. The new int var, the new bool var, is up to the constraint programming tool to find the answers. It will have to assign every single variable I tell it about. It'll have to give it a value. So that's why you make constraints, to force it to pick good values, or values that at least make sense. The constraints have to do with making sense. It's not really what the goal is. The goal is you minimize or maximize something. The variables are for the constraints. So whether or not this rectangle is in the strip or rotated in the strip, I don't know, but I know it's true or false. So these two variables represent the two cases. Next, if one of these variables, well, if the in strip is true, then the strip height better be the height of this rectangle. And if it's rotated, strip height better be the width of this rectangle, because it's being rotated. So that's a constraint, our first constraint actually. So a constraint is established by the add command. So back over here you see add. This is kind of the command that does the most probably. So basically it says, give me a constraint. That's its documentation. It says add this kind of constraint, so you can go look at that. And this is pretty much what we're doing. The documentation is really terse, so it's hard to get a grasp sometimes of what you're allowed to do. But you can say this equals that, this is less than that, or whatever. So what we're going to say is a bracket I, so that's the width, is equal to the strip height. And we're going to say model b bracket I, which is sorry, a was the height, b was the width. Like that. So that's a constraint. But hopefully you're thinking, well, that's silly. You're requiring every rectangle's width and height or the strip height, which is not going to work. It'll just say infeasible, which means can't solve, because the constraints are too much. So we need to say, actually, a bracket I is strip height when only in strip vars for this rectangle is true. So we say only enforce if in strip vars bracket I, which represents the true or false for this rectangle being in the strip. So here's a constraint that is conditional on a Boolean variable. When this is true, it will then enforce this. And if it can't enforce it, it'll make this thing not true. And then likewise, we're going to use the rotated form only if rotated in strip vars I. So that's the constraint we want. We're not going to say it must be the case that in strip or rotated in strip is true. We don't really have that situation. It's allowed to not include one of the rectangles in the strip. But in other cases, we will say it's got to be one or the other. So you figure out which one it is. And if it is this one, then this thing applies. If it's this one, this thing applies. But that's not our situation. We don't require one or the other. You could just not include the rectangle. So that's our constraints. We've established everything we need to know about this problem in a trivial amount of code, frankly. And the last thing to do is just say, okay, what's the goal here? Are we trying to make as many of these true as possible, or make this as large as possible, or what's going on? And the goal actually is maximum number of rectangles. So we want to, okay, I'll answer that question in a second. We want to know how many of these either or can we make true? They're Booleans, they're true falses, so they're really zeros and ones. That's how it works behind the scenes. So if we add up these boolvars, we're either adding zeros or ones. And if they're ones, that means they're true. And so then now this is enforced and so on. We will be getting the count of rectangles in the strip. So if we're going to maximize that, we're going to say model.maximize, and then we'll call the Python sum function. And we have two lists of bools, so we'll add them together, which makes one big list of all of them. So this means count number of So maximize that. So now it's got a goal. It would have just told us like, oh, everything's false, because who cares? Now you're saying you don't stop searching until you find the absolute largest number of bools that can be true. So now it has a purpose, and it will do its complex search to find the way to make this number as big as possible. Yeah, so Dr. Del Rocco asks, what if you make a circular constraint? And I believe, so I've seen some error messages that give a very, very unusual hint that something is wrong and can sort of point you at it. And you might even see the word or the phrase describing the variable in question. But I think ultimately the most likely scenario is it'll say infeasible. It's like, just can't do it. There is no way to find out what caused it to be infeasible. I've actually looked this problem up. The author of OR Tools, at least this constraint library inside OR Tools, has said really the only way to find if you've got bad constraints that make it infeasible, you have to take one away at a time until it's feasible again, until it gives you solutions. And then you'll know which one broke it. But it's, it could be like a combination of constraints that break it or whatever. So it's very, very hard to debug this. You do not get to stop it halfway and say, tell me why you didn't work. It just says no. So it's rough. So now we call the solver. We say, or we make a solver object because we can give it parameters. Yep, exactly. We're telling it, here's our problem and constraints, as constraints and variables. Now you go do it. And you'll see that here. So we say, I'm going to have it give us progress as it goes. You can also give it time constraints. Like in the tool that does the course planning that I made, I have to give it a constraint of like a couple seconds. If it can't find a solution in a couple seconds, just stop. And usually that means it finds a solution that it's not completely sure is optimal, the best solution. But usually you can just run with that solution. So, and then we're going to get the status after telling it to solve. And then we'll print if it's got a solution. Get some statistics. I think it actually already shows that with the progress. And now I just want to know, like, for all my rectangles, did they get included or not? So I'll go for each rectangle position if, and then we ask, hey solver, did you set the variable to true? So you can't just go look at the variable itself. It'll just say, I'm a bool variable. You need to ask the solver, which is the thing that holds the solution, what did you set the variable equal to? So if that bool that represents just putting the rectangle not rotated, we'll say what the dimensions are. And if it's rotated, we'll say it the other way. I might switch A and B at the end there, I'm not sure. And that's pretty much it. Yeah, let's switch A and B. All right, so again, we set up the initial data, created a model object, made one variable for the strip height, which is something we don't know the answer to, but it'll be used in a constraint. Then we set up a bool, a pair of bools for each rectangle. Are you included or are you included rotated? And if you're included, your height needs to be strip height. If you're rotated, your width needs to be strip height. Otherwise, no, we got nothing to say about strip height. Maximize number of included rectangles and solve. So when you run it, rotated in strip not defined. Rotated in strip vars. So it solved it. It's a very small problem. So in strip 3 by 2, yes. 2 by 2, yes. 5 by 2, rotated. So we matched their answer for the first one. I'm sure you could solve this in the usual way with a bunch of nested such and such, but this is a lot more fun. You don't even have to think about recursion if you use this approach. Let's use their second example. Two by 1 and 3. 2, 3, 1, 3, 2, 3. Oh, same things. All right. By the way, it says the objective, which is the sum of the boolings. 3 by 3 and 3 by 3. That's what they got to. So we match that solution, and then we'll try this one. Four by 2, 4 by 2, 1 by 2. That's interesting. I think there are 2 ways to get 3 of them. It'll always come up with the same one. Yeah. So I think they have this solution, but they don't report there actually is another one that has 3 rectangles in it. There's a 4 by 2, right? Yeah. So I think we just found a different solution. That's the same number. Yeah, Dr. Del Rocco, that's great to answer those questions. Indeed, I don't know about this particular problem, but a lot of these problems are NP hard, meaning there's no efficient solution besides like the exponential search, the complete search. So that's what this library is for, is to better handle those problems. And it can find solutions faster, not order of magnitude faster like polynomial time necessarily, but it is optimized to solve those really hard problems. So for that matter, what if we randomly create a pretty large array I guess we'll do this. I guess it's not very large, but still. So a bunch of random stuff. Now we're not going to know what the answer is, but we can at least run it. That was still too fast. So let's go bigger. It actually has a pre-solve step where it tries to simplify the problem. Right here it's showing, okay, the best it found is I can only fit 2 rectangles, so my next area to search is at least 3. And you see the upper bound is decreasing as it realizes in its search, like, well, that's not going to work. I can't get 19,000. I can't get 18,000 rectangles. So I don't know how long it's going to take, but I gave it like 100,000 rectangles. But this is a little more realistic for what they use it for, things that take hours or days. Now, I've not solved this the traditional way. I don't know if this is faster or not, but I don't really feel like solving it that way since this is already done. All right, so if you stop it, it says, well, it's feasible. I did find something that meets constraints, but all I found so far was 2 rectangles to put in, and there's a lot more to check. Now, other times, this is interesting because it went down by 1 every single time. Most problems, it can cut a whole chunk of possibilities off and say, those are all worse than what I've seen, so I don't need to investigate those. This one's interesting because maybe the way I set it up, or just this kind of problem it had to go 1 by 1. All right, so that's that. Let's move on. Another one called Rubidium 2018. Okay. Oh, by the way, we don't have the inputs for their challenge, unfortunately. I'm not sure what this 3 minutes is. If that's runtime, I don't think a person typed a solution in 3 minutes. So maybe it's runtime, but where were we? Okay, so this one says, given points on a grid, find the minimum distance between some pair to maximize another metric. Okay, that's not very interesting. So there are n sheep on the field, which is so big, and they each have a shade, and the shade goes, rectangular by distance d. So actually all shades will spread out size d. And the question is, they can't overlap, by the way, these shades. So you can't just make d as large as you want. And what's the largest width and height they can spread it out? So if they start as little points, and then they're going to spread out their shade the same, all directions, the same amount until they start overlapping, and then they can't do it anymore. So if you know their positions, you don't know how much they can spread it out. And it has to be integer positions, which is good because the techniques we're using only support integers. So this doesn't spread out anymore, for example. So how much can they all spread out if they have to spread out this equal amount? So again, if you're going to solve this traditionally, you're going to do some sort of looping process where you keep track of, it's like a tree search probably. You say, well, let's spread out halfway, like, well, I started at a number like 5, and then does that work? And if it does, then you can maybe spread out even more and you do your checks and all that stuff. But what we're going to do is represent it as constraints. So we're going to start by making our variables, actually making our data. Initial data 0, 0, 10, 10, 0, 10, 0, 10. So those are the XY positions of these four things, and we don't know what D is. So D is our first variable. Got a range up to, I guess, I don't know, 100,000 maybe. And it's called D. We need to go through each XY pair. And now we need to ask ourselves, like, what can we use to represent the problem? So we don't need an int var for the position xy because that's fixed. We do need an int var for the distance, which I just made. But we can't represent a constraint yet with just D. We need to represent a constraint about overlapping. So we need to look back over here and see what do we have available to us. And there is something called no overlap 2D. So that's exactly what we need. No overlap 2D. This constraint ensures all present rectangles do not overlap on a plane. Each rectangle is aligned with x and y, defined by two intervals which represent projection on x and y axis. So you need to give it intervals. It's like our x's and y's lists, except we need to use honest interval variables for this. So there's a thing called new interval variable, new interval var. So here we go. Instead of an int var or a bool var, we're going to make a new interval var. Interval vars take a start, size, end, and a name, of course. So really start, size, and end. So in our case, the start is, I guess, the position of the dot. Let's just say this interval left to right. Or we'll say width, the whole width. So really the start is the center minus D, and the end is the center plus D, and the width is 2 times D. Or the size is 2 times D. Now, I don't know what x minus D is, because I don't know D. I don't know what x plus D is, because I don't know D. I don't know what the size is, because I don't know what D is. It's twice D. So all these are now a challenge, because I got to give it a start, size, and end. And I don't know what they are. But I can give the integer variables, int vars, for these three things. So I need an int var representing the left, an int var representing the right, and an int var representing twice D. Because I can't put 2 star D for this. It needs to be a variable. So I'll start by making a variable called twice D. Its range is, I guess, the following. And then just doing that doesn't make it twice D. It's just 2 separate variables. So I have to add a constraint that twice D is 2 times D. So it'll force that to be true forever, no matter what D is. And it seems silly to have to write something so trivial, But you have to tell the system what this thing is for. And I have to have that thing, I have to have a new int var because I have to give it here. I can't put a formula here because it has to be either a real value like a simple number or integer variable, which they mean to be a new int var. All right, and then the left side for this shade, I have to make a variable for. And if D can go to 100,000, I guess this can go to negative 100,000 to positive 100,000. So now I can say I've got an interval like that. So that's the interval for that particular shade, number I. The function new interval var requires honest variables here. Now, if you happen to know something like that's always 10, you can give it a 10, but you can't put a formula here. Like, this is not acceptable. So I had to make a variable out of it. All right, I'll do the same for the top and bottom. And that would be a height. So I got to be careful here. Start plus size equal end. So start would be bottom plus size equal end. Okay. So these interval variables exist. But I've got no constraints on them. So I need to say that the position x minus d is the same as left. So we'll add a constraint. Left is the same as that x position minus d, and right is that constraint plus d. And likewise, so luckily they all have the same spread, size D, so the constraint's not too hard to put in. Now I'm going to need to, if I want to use no overlap 2D, I need to collect these in a list for later. So I'll say and then I'll stick it in here. All right, now that I've gone through all the rectangles, or points, x and y, I've got all my intervals this way and that way, all the same amount by d. I can then say, don't let them overlap. Okay, it's all the constraints. Now we need to say, what's the goal? Yep, the stat is satisfiability, which is a traditional representation of these kinds of problems where you only have booleans. So it's kind of like doing this only with the bool vars. All the constraints are established. Goal is to maximize how much you can spread them all out. Maximize that D, which will be the same as maximizing twice D, but probably more confusing to read that kind of code. And then we solve it. I guess the only thing that's interesting is what's the value of D. So that's it. Fits on a screen, the whole solution. Then we run it. It says D is 5 for the first case. Should return 5. Good. This one should return 2, so I got to put in this information. Two. That's what they got. Now let's try a random large one. We have to make sure no sheep are in the same position. So I think that'll do it. Make 100 by 100 pairs. Don't let them repeat. Said it made 120,000 Boolean variables. There were 20,000 intervals involved, 40,001 linear constraints. That one was the D equal 2 times D. It ultimately restarted the search 93 times, hit no conflicts, which is interesting. Sometimes it'll go down a bad path and have to back way up. Took 7 seconds wall time, and so on and so forth. So I'm curious, actually, if we search for this, can we find someone else's solution? Indeed. This one was Rubidium. So goes through all possible x coordinates. Or no, I think that's the input. For all y coordinates, find the closest point where x is the same, as only y is different. While, so third loop, find new points with different x that have delta y. And then a for loop inside of that, and a for loop inside of that. So I don't know the complexity of this particular solution. I argue our solution is easier to read and understand, but maybe not everyone feels that way. I wonder if we can find, I don't see any others. But we'll keep this open. So now there's 200,000 intervals. I don't know how long it's going to take. You can force it to stop if you do. Control-C 3 times. So it'd be interesting to measure how long it takes to do these different solutions, and maybe against this one as well. This one's a greedy approach. It's too slow. So I don't know how Codility checks speed, but this one doesn't backtrack. I don't think the other one backtracks per se. I think it just searches everything, but I'm not sure. All right. So what else is on our list? We'll do, actually, let me see. I have another one that uses int vars. And another that just uses boolean. So let's do the more complex one. We'll do this one, and then we'll do one that I haven't solved yet, or don't really know how to do. This one is the Palladium 2020. Given n rectangular buildings of width 1, so basically just heights, right? The buildings don't have any width, so you don't have to think about that. They're just tall, a certain amount tall. Find the minimum total area of 2 banners that will cover them all. So if you got buildings at different heights and you only have 2 banners and you want to optimize the space, so you don't want to like have a bunch of extra banner when you don't need it, what's the minimum area of all the banners combined? There's only 2, but still. So you see here, you can stretch over the height 3 and height 1 building with the 1 banner, and then stretch over the height 4 building. If you use, if you only use one of the banners, it has to stretch the whole way, and that's wasteful up here at the top. Likewise, if this one on the right stretches further, it's also wasteful above this middle building. So this is the optimal configuration. Sometimes one of the 2 banners, we can say the second banner isn't even used because it's optimal to just have 0 width. Or it doesn't matter, it would be the same, maybe. And here's another example. So that's the challenge. Basically, it comes down to what's the cutoff point for the first banner. If you think of the green banner, how far does it go? That's a variable that we don't know the answer to. If it goes 0 amount, it means the second banner is taking up the full space. If it goes all the way to the right side, it means the second banner is not being used at all, or it's somewhere in the middle. The height of the 2 banners is dictated by how much it has to cover. So if the first banner covers these 3 buildings, its height is dictated by the fact that the tallest building in that 3 is 5. So it has to be equal to 5. I guess at least 5. And likewise on the right side, if it's covering these 2, it takes the height of the maximum height of the buildings it's covering. So that's the constraint. And then the optimization, if we compute the area as the width and height of the banner and add up with the other one, we want to minimize that sum. So we have all the pieces. Now we just have to figure out how to type it out. But what's nice about this approach is you're defining and representing the problem, like as an actual statement of the problem. We could we could say what I just said. Like we can write it out as these are your constraints, these are your variables, and this is the optimization goal, minimize or maximize something. So you're kind of just redescribing the problem as a statement of constraints and variables and goals. Unlike what you're forced to do when you write traditional code, you have to go through all this issue of indexes, lengths, for loops, appending things and keeping track of things and functions. And so it's like it's getting lost in your programming is mixing up the actual problem with issues about structured programming. Here we can just represent it as it is, as an actual, like close fidelity to the original problem. So what we need is to represent where the first banner stops, fundamentally. That's the main question. Heights. The only information we're given is the heights, so 314. So the question is, what's the width of the first banner? That's a variable. And we'll say this banner cannot not exist. So it makes the problem a little easier to represent in code. This banner will stretch at least 1, maybe all the way across. So the min will be a 1. Because it doesn't matter if it's the left or the right banner that stretches all the way across, if it does stretch all the way across. So we'll just let it be the first banner that stretches at least 1. And the most it could stretch is however many buildings there are, which is the length of the list. Now the height of the banner, I don't know. It's a variable. Got to be at least 1. I guess you could say the max is whatever the max of the heights of the buildings. That would save it time searching. I wouldn't be trying heights that are no good. So we'll say that. And then we're going to make a variable for banner 2 width, but then we'll actually constrain it because we kind of know what it's going to be. It could be width 0. Turns out banner 2 width has to be the width of the, or how many buildings there are, minus the banner 1 width. It's the leftover width. So that helps because there's really no reason to let the solver try numbers for the width if you know what it's supposed to be. If there's a rule about the problem of what this width has to equal, give it as a constraint so it doesn't go off in some search that's ultimately worthless. And then it has a height. Now we want to minimize area, so we have to calculate area. Since I'm using the max a lot, I'll say max height ahead of time. Okay, so the area could be at most max height times max height, I guess, or max height times the width. And likewise, but it could be 0. All right, so we made variables for the area, but we need to say what it equals, that it is the width times the height. So we want to say banner 1 area is equal to banner 1 width, banner 1 height. I'm going to run this. Yeah. We get an error. That's not allowed. You cannot multiply two variables. Not with this approach anyway. This is not a linear expression. So recall the add command says add a bounded linear expression. It's bounded, by the way, because every integer variable has a limit, min and max. So that helps it search, but linear expressions are variables perhaps times a scalar being an actual number, not another variable. So 2 times x, 100 times x, or whatever, plus y, plus z, greater something else, minus 5, whatever. That's all fine. X times y is not the same thing at all. That's not a linear expression. They're much harder to solve with. So they have a separate command for that, a separate function. Multiplication equality. This is a constraint that says the target is going to equal the multiplication of these other things. So target has to be an integer variable, and the variables involved have to be integer variables, and it adds this as make this true at all times. So when target changes, if for some reason the area changes, then it's got to go figure out what do I have to multiply? How do I have to change the variables so they still multiply to equal that? So any of the things involved here, either the variables you're multiplying or the target, could be changing for different reasons, and it has to keep this true. So we're going to say multiplication equality, and you give it a list of things to multiply. Then we do the same for the other. Okay, so that's a constraint that keeps that true. Now, so we have areas, and then ultimately we're going to say minimize. And again, you give it a linear expression, but this is linear. So that's okay. Addition is fine. But now we need to deal with the fact that we need to put some sort of constraint on what these heights and widths mean. So this is the only part where it really gets interesting. So we'll say for x and h and enumerate heights. So enumerate is a Python feature that will go through this list and give you a pair of things. It'll give you the number from the list, that's h, but it will also say what position it is, 0, 1, 2. So we want to kind of keep track of where we are. This is our x position because these are heights of buildings, 3, 1, 4. X is 0, x is 1, x is 2. So we're going to use the position in the array as the position of the building. So for each position of the building and each building height, the question is that covered by banner 1 or is that covered by banner 2? It's got to be covered by one of them. So that's the goal. We got to make that constraint. And if it is covered by banner 1 has to be at least that tall. If it is covered by banner 2 has to be at least that tall. That's the other part of the constraint. So we first make a variable covered by banner 1, yes or no. Bool var. I'll just make a message for myself. It's this particular building. I guess I'll say building. And you could also be covered by banner 2 instead. So those will be true or false. Now, the building in question at position X with height H has to be covered by one of these two. So we need a feature of the solver that says one of these has to be true, and that's the bool or. You give it the list of things that need where one of them has to be true, and it will make one of them true, at least one of them true. So that's a constraint. To force one of those to be true. Now, I don't know if it's going to come out in the fact we're minimizing the areas or what, but it might even help it solve if I tell it, because really you want to put as many constraints as you can think of. The more constraints you have, the faster it solves, because it won't try silly things that don't make any sense. So it is true that if banner 1 covers that building, banner 2 is not covering that building. So I want to say, if it's the case banner 1 is true, make banner 2 not true, and vice versa. You can say not on a boolvar. So implication is a feature that says if the first one turns out to be true, then the constraint here is then this one can't be true. And then vice versa. I think I want to do it that way. Now, I don't know if they are true, which one is true, but at least I can say this constraint is accurate. Now, if you are covered by banner 1, well, then you have a constraint. Banner 1 has to be at least this tall, and banner 1 has to cover at least up to position X. So actually, I guess we're going to go beyond position X, because if you're going to cover first building, that's X0, but you want to make it go all the way to position 1. So we'll say less than banner 1 width. And like before, that's not universally true in every situation. That's only true if banner 1 is covering this building. So only enforce if covered by banner 1. And then the other thing to say about it is the height. Banner 1 has to be at least that tall for this building. Only if the banner 1 is said to cover it. And then likewise, we'll do all this for banner 2. So I think that's all the constraints. Dr. Del Rocco, do you mean down here where you can only say a variable? So minimize also accepts a linear expression, just like add, regular add. But if you're making a new int var or something like that, you just give numbers. Model add, less than. Yeah, so, okay, linear expressions can have inequalities. Less than, greater, less than, equal, greater, not equal, and equal. No, it's a good question. So let's tell it to solve. Now, when it solves, you can only print out values for variables you have represented in the system and that you've been keeping track of. So I can print the areas. I can't print for each building whether it's been covered by banner 1 or banner 2 because I didn't keep track of these. I need to make a list. And make sure I put them in the list. So with that, I can now go through the list. That might be enough information to make sure it works. Banner 2 both are all times. So yeah, whether it's banner 1 or banner 2 that spreads the whole distance is not relevant, but it's the same banner. So there you go. That one's right. And the total area is 4 by 3. We can see that as the objective. When you say minimize or maximize, you're calling it that, you're saying what the objective is, and so it'll print the objective value, which is the sum of the areas, so that tells us what we need to know. If it's covered by banner 2, what do you mean by that question? Or maybe I've changed it already. Let's put a different problem in. 314. Oh, we did that. Wait, is that the same? Wait, was that not optimal? Maybe I've coded it wrong. Should return 10, not 12. Number if code by banner 2. Ah, yes, that's probably why we got the wrong answer. Good catch. Notice it was perfectly happy giving us wrong answers. It considers them optimal. It doesn't know the difference. So thanks for that. That's why we probably got that wrong. So I'm still getting it wrong. X less than width. Oh, you know what? I think I had this problem the first time I solved it too. So, challenge to the group, where is the issue? There's still a problem. So the problem is, if you're covered by banner 2, you have to be to the right of the starting position of banner 2. And I've coded it like your banner 1 to the left. Banner 2 starts in the middle. If you're covered by banner 2, you got to be beyond that. So this goes the other way. Access be greater or equal to banner 2 if banner 2 is covering you. So if you do that, you'll get the westbound 3. Oh, we have yet another problem. it's willing to make banner 2 start, stop, and start again. Let's see if we can figure out why. Check on my 1s and 2s. Actually, I still had it wrong. X greater than banner 2 width. So banner 2 width is always the total width minus the width of banner 1. So that's actually not relevant to us. So like here, banner 2 width is 3. That doesn't mean banner 2 starts at 3. If you're in banner 2, your start needs to be after banner 1's width. So it's not completely symmetric, these constraints. That has to be a 1. It has to be greater than equal and has to be banner 1. And we do want greater equal because, for example, in this case, banner 1 would be considered to stop at 0, which makes banner 2 start at 1. So, and the width would be a 1 for banner 1. So banner 1 is always width 1. Sorry, I shouldn't have said stop at 0. Banner 1 is always width 1, which means at position 1 is where banner 2 starts. So we do want to allow X to be the same place banner 1 stops. So with that, we get the 10. So we get their solution. And let's try this one. Objective 30 should return 30. So I think we've solved it now. 1 and 1 and then 2, 2, 2, 2. 1, 1, 2, 2, 2, 2. All right. So this showed bools and ints, multiplication, and implication, and OR conditions. So let's try something I don't have any code for yet. Let's say, got two options here that I looked up. A lot of these have to do with string manipulation, like reordering strings, and that just didn't sound fun to represent with this tool. So I'm trying to focus on ones that are kind of like matrix and array stuff. So there's this one which says there are glasses of different sizes, each contain a different amount of juice. They all each glass contains one kind of juice, and so there's different amounts of each juice. And you have another glass that's a certain size, and you want to see how many juices you can mix together but not overflow the glass. So that sounds like there's got to be stuff here that handles that. There are things about reservoir constraint, but this is probably more complicated than we need. This is about different times. There has to be at least a certain amount in each reservoir. And so things can change amounts, like they're a bunch of wells or something, or buckets or whatever, and you can take some out of this one and put it in the next one, but it's got to maintain certain levels. That sounds more than we need. What else do we have? Cumulative. That has to do with times again. It might be as straightforward as basically a packing problem where you say, so there's these juices, they have this much juice. Oh, your function should return to Rick can pour third glass in the second one. Third glass into second one. There's still space in the second one. And so this one says 3 can pour from 0th and second into the first. I don't get that. Jth glass is capacity J, contains J units of juice. So in this one, he's pouring, oh, into the first one. Sorry, that would have been this one. So the 1 and the 3 can be poured into the 2, which adds up to 6, which is the capacity. So there's that. The other one I thought of from this list is this one. Companies and developers wants to divide them into 2 teams. A team called F, and the second team has N minus F developers. And if they're in the first team, they contribute this much. And if they're in the other team, they contribute that much. What's the maximum sum of contributions overall? So that sounds similar to what we've done before. You're basically saying, for each developer, should it be the first or second team? And they'll contribute this much. There's only 2 positions in the first team. And you want to maximize the sum. So, does anyone have a preference? I'll think about this. Well, I'll see if you have a preference. All right, we're doing the juice. So, capacities and units. So, to recap, the capacity says how big the glass is, and this says how much juice is already in the glass, and you're reassigning. And when you reassign, like if you move this into the first glass, it all goes. You can't take partial. So what we need to know is for each glass, is that juice going somewhere or not? And then where it's going, everything that goes to that same place, you got to make sure it adds up to less than or equal to the capacity. And then we'll figure out the maximize question after that. So for each juice, does it add to itself or go somewhere else? So I guess if you're adding the two to say you're adding this one to the first glass, so everybody's going to the first glass, you could say the first glass is going to itself also. So every glass could be said to go somewhere. And the first would go to itself. It's not that the first doesn't move. So others can just go to themselves as well. If they go somewhere else, do we even need to know their capacity at the end, that they're 0? So, mellow, cello. Do you have an idea of the approach? Or are you just talking about the question statement? Okay. Let's at least represent. So the capacities are fixed, so we don't need to represent that, but we need to represent the sum of something. So the sum of all the things that are going in the first glass needs to add up to less than or equal to 10. So how do we represent the sum of everything going to the first glass? Ooh, you know what might be relevant? This is interesting. This is where it really gets puzzly, because there's actually a thing I think we're going to use here that's not really what you would expect. So if we need to know which glass does each juice go to, we're giving each glass a number. You go to this other glass, which could be yourself, I guess. So I think what we need to know, and then we need to look up for the glass you're going to, what's its capacity. So I think we're going to use this guy. Add element means add element constraint. Add a constraint that works as follows. Of a list of variables, pick an index, which is, position, and make the value in the list at that position equal to this third thing. So it's a way of us grabbing what it chooses that position to be. So it's choosing the index. Among this list of variables we give it, where in the list it's making that choice. So I can't see that choice that's making unless I make it this variable. So let's just make a list first of all the things we have. This is called multivitamin. So for each juice, I think we're going to want to know where it goes. destination glass. Possible positions are, the length of the array. So I think we want to say add element. Variables are clearly, wait, I'm not so clear. We want to know the capacity of the destination. How do we collect all the destinations and add up their capacity, add up the amount of juice though? Think for a minute. So suppose we have something like actually, what's the solution of that one? That one is should return to Rick can pour third into second. So 10 goes to 10, I guess. 2 goes to itself, third into second. So this one goes to itself, and this one goes to 2. Third gets moved to the second. So we want to have some sort of constraint that says capacity at 0 is less capacity destination glass that go to 0, sum to, so juice is at destination glass at I add up to less than or equal to capacity at I. So for every I, add up all the juices at the destinations that share that I and make sure they add up to less than equal to capacity at I. Don't know how to get them all together so they can be added. So if we take these as positions in juice, how do we add them? That's where the puzzle comes in. Like, I can do it with a loop, but I can't do it yet with this constraint system. I don't know how to collect the things that share the same destination class. I mean, I can see them in an array, and we can walk through them for, for I and destination class and then check if it's equal. But how to make the system grab all of them at the same time. I know how to grab one of them with this, so I can ask, what if that's the destination glass you're using, I can tell it to get the capacity of that glass as another variable. But how do I get all the capacities? I mean, I can say the capacity has to be at least that big, but that doesn't help. I need to add up all the things that go in that capacity. And you can't make a constraint that simply collects things in a list and then do something with the list. You have to collect that list yourself before you run the solver. So you can make a list of variables, but you can't have it build a list of variables as it's going. I guess, yeah, that's right. As it happens sometimes, you're like, oh, that's got to be easy. And then, wait, I don't have any tools to do this. Let's see what else we can do here. Decision strategy. Search strategy, we probably don't want that. Cumulative. Sum. Okay, wait. I said this was useless before because it had to do with time, but we might have to reinterpret this because look at what it's doing. Adds cumulative constraint, capacity, demands, intervals. Not sure about intervals. Maybe I can make intervals of size 1. Yeah, I was thinking too about array of bools, but I'm worried about an array of bools needing to be the size like a matrix of bools. So for every glass, I need to know for every other glass, did you go there or not? And so it's an n by n matrix, which I'm somewhat worried about getting too large. I think I could definitely do it that way, but it might be too large. Let's see what this cumulative thing says. For all t, whatever t is, the sum has to be greater or less than equal to capacity. That sounds good, except I can make a cumulative constraint per glass because they have different capacities. And I know the capacities up front, so that's not even a variable. I guess it could be a variable, frankly, but I don't need it to be a variable. I don't think. Maybe I do want it to be a variable. But the sum of demands, which is a list, at position I. Now, what does this mean? Sum demands if start and t is present. So I guess the demand is only in play. So the demand is like how much juice. I'm demanding this much space because I'm going to move my juice to that position, I. Or no, that demand is number I. Interval t, I'll have to think about what t is. So the demand I is the amount of juice at glass I. I demand to put this juice somewhere. If start intervals t, so t is between start and end, and it goes through all t. T is present. What does present even mean? It doesn't mention t or present anywhere else. Arguments, list of intervals. List of intervals, or list of demands for each interval. So are my intervals just glass by glass? I think. Each demand must be greater than or equal to 0. Each demand can be integer value. Capacity, maximum capacity, cumulative constraint. List of demands for each interval. So again, the demands would be the juices. If t is present. I don't understand t is present. See if anyone's used this. This is the author of the library, by the way. He answers a lot of questions about it. This only shows one argument. Not seeing the use of this. So now there is an interval optional interval var. Creates an optional interval, and you can say Boolean variable if this is present or not. So we could say the juice is going somewhere, yes or no. So this could be turned true, so this interval exists, and the start and stop could just be literally the juice's position, like 0 to 1, and 1 to 2, and 2 to 3, and so forth. And it has a certain demand for that interval, so these would agree with each other. List of demands for each interval. I don't know what the T is. It seems like it should be for I, but oh, I guess T is like a made up thing. It just finds all the T's that fit between the intervals. So in our case, so you don't give T as a parameter, it like goes through all the possible points between the intervals you give it. So in our case, it would just go left to right through the array positions. So it would add up demand. I feel like that should be a T there. Maybe it just means for that particular interval. I don't know. The demand for that particular juice, if it's present, and all the demands have to add up. I don't know if this is going to work because I feel like those intervals need to be more than size 1. Yeah, maybe I'll do what's been suggested here. Bool vars to say this is or is not moving to that position. Let me just look one more time at the things we have available. Yeah, in this case, this reservoir constraint seems like the current level changes by demands. It adds up. Some of demands I if times I is less than or equal to t. And it has to be within a certain range. So we could just say 0 to the capacity. So maybe each class is a reservoir constraint, and the demands I of times I is less than or equal to t. I worry about this less than or equal, like it's going to include too much. Going to include the whole list of classes. So let's go back to the Boolean approach. So what was suggested is probably best. Yeah, let's just say for each juice, for each class, do you move to it or do you not move to it? So destination class would be a new boulevard. For I and juice, for j and juice. So are you moving to that class? Juice is moving to class. It's in range. I guess we're going to want a 2D array, right? All right, well, let me think after this works if we can not make it n by n. So yes or no, this boulevard, does this juice move to that class? And so far, I don't know of a constraint to put on that. It's more that we want to say, so those who do move, they've got to add up correctly. So let's make all the boulevards. Now we'll say let's take a row. All the trues in this row mean that juice is moving to that class. So, and this row represents this class. So we have a bool array, the row, bunch of trues and falses. We need to multiply those trues, which are ones, and the falses, which are 0. Multiply that array against the juice array to see how much, and then sum it up to see how much we're putting into this class. So we need in C++ version, it's called scale product. Yeah. Yeah, so this is what we want, I think. We want to say this whole list times this whole list. The coefficients list are known values. So it's not a multiplication equality kind of situation. And these are the variables, and then it adds it up. It's a scalar product. So we make that serves as an expression. So we'll make a variable capacity moved, I guess. I suppose nobody can move here. And then whatever, some big number. And then that equals scale prod. How do I represent scale prod here? CPU model linear expression scale prod. Okay. Scalar product expressions would be the row. Those are the trues and falses, ones and zeros, and times the juice. Then we need to say that capacity moved needs to be less than or equal to capacity at I. Now we got to make sure our juice doesn't move multiple places. So it should only be true in one position in the row, right? Either it can move to itself, but it can only be true once. And they're ones and zeros, so the sum of the row has to be 1. No more, no less. It allows you to call Python sum function. It knows how to interpret that as a one of these things, as a linear expression. So you have to move somewhere and only one place. And everybody that moves to you, you get the sum of their amounts. Do we need any constraints vertically that every glass has something moved to it? I don't think so. So I think that's all the constraints. And then we constrain the capacity. So what's the goal again? Maximum number of flavors that can mix. So the maximum number of trues that are not themselves. So we need to add up how many times the true was not its own position. So I think we'll say let's just keep another list of variables. There'll only be as many as we have juices to say if you move to yourself or not. That'll be true or false. And then we'll say if j is I, you move to yourself. So this is an interesting situation. Maybe we can say move to self I is the same as destination class row I. Is that true? You move to yourself if the entry in this row, well, that's not really what it's saying. Moving to yourself is the same as this entry in this row being what it is. So if the entry in the row is true, you move to yourself. The entry, this position in this row is false, you did not move to yourself. I think that works because we know you moved somewhere. So being true or false in this position, which is your own position, is the same as moving to yourself. Why was I doing that? I want a maximum number of flavors. So I want to subtract as many of these scenarios. So I want to add up how many truths there are and then minus these specific truths. Sum of the whole thing, which is a list and a list. So I want to do sum of boolvar for boolvar in row for row in destination class matrix. By the way, what that is really doing for boolvar in, I think it's doing that minus sum of move to self. So discuss amongst yourself if you think that's going to work. This is Dr. Del Rocco. Why do we care if you move to yourself? Because if we only look at the truths in the matrix, we know every row has one true. So we know exactly how many truths there are. So it's always the same number all the time. It's how many juices there are. Everybody moved. We need to know if you move to yourself so that we can subtract the cases that aren't the interesting ones. I got a problem. Line 16. Out of range. Move to self I. Oh, I probably need to move this out of that loop because it hasn't filled up the row yet. I need to move that out of the loop too because it hasn't filled up the row yet. So let's fill the row completely first. Can't add plus or int in list. What do I have wrong here? Boolvar for boolvar and row for row. Maybe I got the parentheses wrong. No. Boolvar for boolvar and row. Why am I typing that wrong? Oh. int x for line and date, int x for row. I think I got it backwards. For row in destination class matrix for boulevard and row. So boulevard for row from destination matrix and boulevard from row, I think. Yeah, all right, so list comprehensions are great, but when you put two in the same, it seems to read backwards to me. But boulevard for, yeah, anyway, I don't know if I can explain it. But what we got, just 0, move to 3, move to 3, move to 3, move to 2. So actually we'll say if it's yourself, we won't print it. Cassie, which program are you talking about? Vim? So what do we get wrong here? Juice 0, move to glass 3 for some reason. That's not possible because 0 and capacity 3 is not acceptable. So our capacities are messed up. For each row, linear expression scalar product, that row times juice has to be less than capacity. I guess we can print the capacities, make sure it knows the right things. I need to save these. Up here. So Cassie, I've used OR tools for one specific problem a lot for like 10 months or something, just refining it. And then I solved these other Codility ones separately. I think I maybe done one other OR tools problem, but I don't know. It's not super extensive, I guess. Capacity for glass 0. So it thinks the capacities are all ones. So that's a problem. Why does it think all the capacities are ones? Let's just print the actual array or the matrix. So I gotta convert this to an int or a string. It's a bool. Yeah, it thinks they all went to the last class. So it didn't add up correctly here. because it should have multiplied. Oh wait, maybe I'm thinking rows and columns wrong. I think that's true. This needs to add up to capacity vertically. Do you all see that? If I'm adding up, I'm checking how much is in a glass by looking across, but that's just one juice at a time. And so it always says, oh yeah, you're less than capacity for sure. I need to add up vertically. All the ones that went to this glass is the vertical. That needs to scale, or be the scalar product. So I need to go down by the row, or sorry, by that column. So juices here for J in range length. Juices here append that column from matrix. So it's that column that we multiply in. The trues vertically. Still didn't do anything. Juices here, pin, destination, matrix, ij. So iterating juices, not capacities. Well, they're the same length, so I'm really just getting a position. All right, I think we're like super, super close if we can just figure out why it's not multiplying correctly. It's right here somehow. So I is the row. So we're on a row. Let me say for each j. Oh, it's not. Is it? I'm getting confused with i's and j's. Let's go j and then I. That might have been the problem. I think I was just going across the row again. Because of the ij ordering here. So I really want to go per column. And then for that column, this is J. Juice 1 moved to 3, juice 2 moved to 1, juice 3 moved to 2. So that one didn't move. Can pour third into 2. It thought yeah, Dr. Del Rocco, they're all the same length, juices and capacities. Why did it move this juice or sorry, the second juice to the last position? Juice 1 moved to glass 3. Capacity for glass 3 is 2. Did it like flip it for some reason? They just swapped places. Juice 2 moved to glass 1. And juice 3 moved to glass 2. So that's right. 3 moved to 2. What's the actual sum? Number of flavors. So there's 2 flavors, I guess. They all switched positions, though. That's interesting. Maybe we didn't make the maximization correct. Nobody's sharing a column now. So we'll check the maximize. We want to maximize the number that didn't move to themselves. Isn't that the same as minimizing the number that moved to themselves? They all have to go somewhere. I think that's right. 3 moved to 1. So there's 2 of them in position. In this position. 1 of them moved to it. Or I could do it the other way around. So the 2 there is actually kind of the answer, but it's the same as minimizing the number that moved to themselves, I think. Or maybe we just want to find the best sum vertically. What's the largest number we can add up vertically? So we can just add up those numbers here. We could say maximize. So if we count the rows, what's the largest count we can get? That doesn't seem right. That guy's largest count was 1. Pen, model, new and var. That variable is the sum of juices here. Yeah, Dr. Del Rocca, I think you're onto something there. So we don't need to know if you move to yourself. Let's take that out. So why is this not going vertically? Shared move R is a pin. It's got to be at least 1. Could be at most the length of juice. Juice is here. Surprised it's not maximizing that though. Why did I minimize? Is that what you're saying the whole time? The max. Sorry. Maximize the max, not minimize the max. It still didn't work. Almost there. Almost there. We'll see. Maximize the largest. Yes, it is an interesting one. It's deceiving, right? It's like, yeah. As you get into it, you realize sometimes writing it this way as constraints definitely makes you see the problem differently. Like, you have to handle the full nature of the problem. Like, you can't miss a constraint because it'll be totally willing to give you bad answers. Whereas if you solve it normally in the normal approach, you'll just add enough code to get a solution that you're pretty sure about. But this is willing to find all the other solutions that your normal code wouldn't even get to, because why would you code it that way? But this will happily find those if your constraints aren't powerful enough. So there's something missing here about either capacity or the maximization. Or the way I'm printing it, but I doubt that. Let's just take off the goal, so it'll just find random solutions that meet constraints. I guess it's the same every time. Maximize shared move. We're printing the shared move. It's printing that correctly. Let's say the capacity doesn't matter. Let's just see what happens. Why is it still thinking that's optimal if the capacity is irrelevant? If you're allowed to go multiple places, then it's going to come up with some random thing, so that's fine. So let's not allow you to go multiple places. I don't have any constraint about going to yourself. It's respecting capacity, but just not optimizing. Oh, I forced every column to be at least 1. Is right here. New int var 1 to juice. The number shared in this column has to be at least 1 because I said new int var 1. I didn't allow any column to have no more juice in it. So I wasn't able to ever, every glass had to go to another glass. Like they all had to switch places, but they couldn't go together because then you would have empty glasses. So I had to allow a column to have a 0, only zeros in it. And the way the sum here says let's add up the column, but that's fine, except that the allowed values for the destination variable did not include a 0, so it was unable to add up to a 0. The length of juice is still appropriate, but we have to allow it to be a 0, like this second column here. So now it's saying this one is adding to this one. So we got that one right. So let's go and do some others. 1, 2, 3, 4. And 10, 3, or 3, 6, 4, 4. So it's taking not getting the 3. You should return 3 Rick and pour juice from 0 and second glasses into the first one. So this and this can go into this. So that went to the other side. That's curious. Let's try this other one, 2 and 3 and 3 and 4. Yeah, this one, nothing can move, so that's correct. And 1, 1, 5. 5 or 6, 5, 8. They can go all together in the second glass, which is the third. So that's correct. This one's wrong somehow. Otherwise, they're all fine. So is this capacity J or capacity I? Per column, left to right, I think it's capacity J. Yeah, there's no I here, so that's right. So it says can pour the 0th and 2nd in the first one. This and this. So 3 into 2 is 5 plus that is 6. Whereas this is trying to say that you can pour the first into the last and the last into the second. It's moving stuff around. Seems like there's actually a constraint that if you pour something in something else, you can't pour that other thing somewhere else, like it's getting poured into, so it has to stay there. But I don't know if I want to put that as a constraint. So running over here, but it's interesting, it only fails this one. I wonder what's going on. The capacities are fine. 6 and 4. I think if you're pouring into a juice, that juice can't pour itself somewhere else. That actually wouldn't be that hard to represent. So if you're moving to that particular glass, it must be the case that the destination glass is true. So that's actually, curiously enough, this add element. We need to get the bool variable from the row of that destination glass. Of those variables, the index. Wait, is this what I want? Yeah, I think so. Of that, or no, the index is glass position. Or no, actually what I want is the row, which is zeros and ones. Only one of them is a 1, so I want to multiply all the zeros and ones by the range going from 0 up to the lengths. So that will make this glass position the number, because it's 0, 0, 0, 1, 0 times 0, 1, 2, 3, 4, 5, 6, 7. So where the 1 appears, that will be the position. So then I want to use that position. If you're going to that glass has to go to itself. So I need to grab that glass. Where does that glass go? I think I have to do this after. Yep, exactly, Cassie. You can't unpour. So you get the position that that glass is going to by calling this destination class row. So what I don't have that row anymore, so I need to say matrix I. So take the row, find where you're going, and then use that to enforce a true value in that position, that I, comma, j. So I guess I do need going to self. Not pouring. And that's true when the true appears in destination class row I, so when it's to yourself. So then you can grab that that bool variable, index would be desc class POS. The variables is not pouring. And the target is desc class unpoured. So it grabs that Boolean variable effectively, and then we make sure that's a true. So if you're getting poured to, you can't pour out. Oh, I should have I, right? Or no, row is just a row. What did it not like? Why does it think it's a list? Not pouring, oh, not pouring I. This particular not pouring variable. And 21 is not iterable. Need the range. So now they're kind of forcing themselves not to pour at all. Take that constraint off, still does that. So destination class is unpoured. So for each row, grab the position, which is which number is a 1 in this row. That's your position. That's where you're going. So then go into the not pouring array for that glass, so 0, 1, 2, 3, so it'd be 3. Go into the not pouring array for that glass and make sure it's true. Index variables target. Yeah, variables at index. Variables at index. It's true. Not pouring is the same as you being the same. Your destination is the same. Oh, that's because I'm requiring it for all the time. I need to do an only enforce if. I think. Or no, maybe not. It should work regardless of that. Let's keep track of these variables to see what they are. Yep, so it knows that's correct. Guess we'll check not pouring as well. So it thinks they're all not pouring. Guess that's correct. So let's think through this from here. Not pouring is true or false. For this class, it's not pouring if its row at its own position is true, or it equals whatever it equals at its own position, and is we don't add this constraint of unpoured, it knows some are not pouring and some are pouring. Sometimes it's 0, sometimes it's 1. That much is true. Yeah, only one of them is a 1. So it knows when it's pouring. So it feels like the issue is pretty much solely right here. It's making them all not pour. Unpoured equal true. It always has to be unpoured. Maybe I don't want it this complicated. Maybe I just want to say, no, I think I need that. I need to know that Boolean is true in the not pouring collection. Or can I just look in? No, I don't think I can look there. So using the position that you pour to, look in its not pouring collection and make sure that's true. That causes this to make destination class row I true. Well, I don't know why it's getting so over-constrained. Might just have to call it, give you a link to a GitHub repo, and see if anyone can find it. Just out of curiosity, if we take out the capacity constraint, I suppose that's acceptable. Nobody's switching positions. So that's sort of interesting. I don't think the two things have anything in common, the destination glass or dest glass unpoured and this capacity. So adding this constraint shouldn't have affected the capacity constraint. what did that say again? So yeah, only one of them's not pouring. So that's acceptable. And it is maximizing correctly. If we add the capacity constraint back in, is it I or J capacity? Yeah, there's no I here, so it is J. Let's try the other ones. Interesting. Nothing's comma-ditto, right? Yeah, so now it's working. It's just that one case it doesn't seem to work on. It's ensuring if you don't move, or sorry, if you get imported into, you can't move. Third glass in the second one, which is the same as what we got because these are both the same capacities and amount. Let's switch to this case. Yep, nothing moved. And then let's switch to 115, 658. They all moved, so that's correct. Just that case in the middle again that we still don't get. Middle and second classes to the first one, or the zeroth and second class into the first one. This and this can pour into this. So one thing you can do to see if it's going to work correctly is you can force the solution for, certain variables, and see if that breaks some constraint. So we want 0, 0, or no, we want row 0 to have its, what do I do? To have its destination be position 1, and likewise for row 2. Let's just try that. Now that works. If I force it, is that because it's the same? It thinks that's the same objective. It thinks it adds up to a 1. So my objective is wrong, not the constraints. Okay, so my objective was maximum of the shared. Wait a second. Okay, I wasn't sure if you had to give max multiple arguments. I'm still not super comfortable. Let's see if they have an example with max. Yeah, I don't know about Python's max function here. I worry about it not doing what I think it's doing. So we can do add max equality. We can make a separate variable. I guess length. And shared move max. Max equality, target, variables, maximize the max. So that still works. I'll take off this forced value. That still works. So did this solve them all? That one's right. Yeah. Yeah. So we finally solved all of the cases they provide. Our objective is actually what they state it should return. So we're getting the right counts for how many things moved. And now I wonder if this whole don't port to yourself business matters. It probably does, but let's just take that little bit off. Interesting. I'm not sure if it matters. Might have added all that don't pour to yourself. I mean, if you're being poured into, you can't pour away from yourself. That might be irrelevant. I guess it's more constraints, which is good for when the problem is really large. Let's try it with a random large set of data. They say it can go up to 100,000. Well, that's how many things. So it could go up to 1 billion. For each juice J, juice less than capacity J. I don't think that matters to us. Or no, it does. The amount of juice less than the capacity for its own glass. So that makes sense. It's going to print this huge matrix, isn't it? Hope you found this as rewarding as me. At least I don't have to dream about it now. Yep, exactly. So something about running model.maximize on the max function in Python of a list of integer variables was not what we thought it was. I've seen that work for some. Something about max is not the same. So it translates Python functions like sum into its own representation behind the scenes. So I wonder why it didn't do it for max. Complex objective functions. That's what we have. Minimize and maximize is complex objective. It's hard to search for this stuff. We may not find source code because it's all written in C++ behind the scenes. So I don't know if we'll find where that translation happens. Oh, here's def maximize. Okay. Set objective. Linear expression. Object, it's not an invar, it's not a linear expression. Or maybe it is a linear expression. Yeah, this could be a whole exploration, but if is expression summary scalar product. Yeah, I don't know why it like passed through, but actually I guess a max is not a linear expression. It still didn't complain though, which is troubling. Sums and all that are linear expressions, but a max is not. That's why I had to make a separate variable for it. So this is taking too long. Let's do a smaller. It's probably the size of this, because you can add so many things to so many things. Yeah, I like your interpretations. It sounds so stupid to have to define some of these things, but that's what happens when you, like I was saying before, you set it up to do the work for you, and you don't get to influence what it does after it starts. You had better set it up as well as necessary, right? It's whatever you need so it doesn't get the wrong idea. And now the question I'm not going to try to solve, but is it actually efficient in what it's doing? How you set up constraints can make it really not that efficient at all. It doesn't seem to be finding the solution very quickly. I found that it can fit 22, it can pour 22 cups into the same cup. It's not sure if it can do better than that. So let's go down even further. 10 cups. Well, that was fast, but interesting. My capacities probably are far too large. All right, so that's more interesting. Yeah, so I'm not sure how this scales, but it does appear to solve it, which is all we can ask for. All right, so I'll post the code developed here. I'll send a link out to the list again, like the announcement, so that you can run this code. I'll comment out these random variations and go back to a simple case. So if you want to run it yourself, grab it from that Git repo. All right. Well, that was an adventure. I hope you enjoy such things, because this is basically how the other problems turned out too. It took about this long. Not all of them, actually. One of them was like 15 minutes or something. But we had to ultimately use quite a few things here. The scalar products, add element. Again, I don't know if it's really important if you port to yourself or not, but that's a little bit obscure in my opinion. Add element was defined in an array. If the position in the array is something the solver is finding out for you, use that to get the value in the array at that position and give that back to me, and then I'll add a constraint on it. So that's kind of interesting. And then the rest was just int vars and bool vars, and to not use max in the objective, because that's not a linear expression. And neither would be min. So I hope this is useful to you later in some situation where you find that it's one of these problems where you have to optimize something. And if you can, maybe if you can kind of immediately think of it as, oh, I bet I could do that with a bunch of bool vars or int vars and solve it pretty quickly, then it might be a good case to use this. The second good case to use this is if you really have a problem that is actually quite large and you need all the fancy tools that this has. But I think you're going to know that and not just think while you're walking down the street like, oh, I should probably solve it that way. You're going to know you need to solve it this way. As for everything in between, these exercises are fun to challenge yourself. Whether this is really the best way to solve it, I don't know. We'd have to measure the performance. And ask ourselves, how much effort do we want to put into thinking about it differently to try to make it faster? So that may take some effort if there's even a way. And for comparison, what was the solution? Which one were we working on? Multivitamin is current one, I guess, right? So do they have multivitamin solved? Is that this gold thing? Yeah. Interesting. Pretty short. But we don't know how this scales either. Interesting. Sorting and so forth. So that there might be clear optimizations that we totally missed by defining it only as constraints. There actually is a technique called where is it? I guess it's the decision strategy. You can guide it to look at things in the right order if you know your problem can benefit from that. Anyway, that's well, so in practice for large problems like vehicle routing or actual bin packing and stuff like that, this would be an optimal way to solve it. You can also, it goes parallel too. You can give it all the cores that you have and it will use up your entire machine to solve it. So like in the case I used it in for organizing courses, that is literally a graph search problem. There's prereqs, there's co-reqs, there's when courses are offered. There's constraints about how many credits you need sometimes. So that was far easier to represent as a bunch of constraints and not have to code up the tree search or graph search algorithm for that. For these kind of things, it's not necessarily a graph search algorithm. You might get away with doing manipulations with arrays and sorting and stuff like that. So it's probably overkill to use what we used. But of course, the exercise is to get experience in this approach. But as far as actually solving problems with it that require this approach, you have to kind of check if the thing you're trying to solve is one of those NP hard problems, like all solutions are exponential time as n gets larger, then this is a good technique because it will trim faster. If you find yourself writing pretty deep and involved tree search, like backtracking search, then I would jump to this kind of approach. But I've only used this approach realistically maybe a couple times for problems. So it's not like an everyday kind of thing. But if you want a new challenge for solving these kind of programming problems that in some cases make it far harder than it really needs to be, but that's the challenge, I think this is an interesting thing to use for that, for the fun of it. All right, so I'm going to take off. Watch the list for a GitHub link, and thanks for joining. I really enjoyed it. I hope you did too. And the recording, I hope to put somewhere as well. And next time with React, it's not going to be this challenging. React's pretty straightforward. So I'll have examples in React and make a little website, and that will be fun and easy. We'll have a martini while we're doing it. It'll be just fine. So I'll see you all later. Thank you.